Well, I'm very glad to be here, and I appreciate the invitation. This is my third time in St. Petersburg. The first time was under Brezhnev, and it was not as attractive as it is today. But you really have a beautiful city here, and I'm very happy to be here. So I'm going to talk about the roots of the subject that's come to be known as differential cohomology. Can you hear me in the back? Yeah, good. And like many things in mathematics, it ended up not exactly where I thought it would start. I just was working, I wanted to learn characteristic classes in one way or another. And so I decided a good start would be to try to understand, to develop a combinatorial formula for the signature of a four-manifold. The signature, as you probably know, is you can calculate it as it's a Pontryagin number. It's the integral of the first Pontryagin class, I think. It is, in fact. And like the Euler characteristic, which is an integral of a form, one might think that there was a nice combinatorial formula for the signature as there is for the Euler characteristic. And so I did what I thought was the obvious thing. I took a manifold and then started to flatten out pieces. It was triangulated, and we started to develop corners and edges and look at what happened to the integral of the Pontryagin form as these edges and corners developed. And things worked out nicely, mostly, but then there was one term that I couldn't really understand. It was a kind of a nice term, but I really wished it would go away. But it didn't. And so it ended up being something that seemed worthy of study on its own. And ultimately it led to, I never did find a combinatorial formula for the signature. In fact, it's still an open problem, although a year or two ago, a fellow came with an algorithmic approach to it, which was pretty good, but it wasn't a nice closed formula or something like that. It was a procedure, more or less, as I recall. And anyone can correct me. Am I right in that? So that's a nice open problem in some sense. So what I'm going to do is just trace sort of the origins of this type of investigation of these, what ultimately became differential cohomology. It says mathematical roots, but it's supposed to say the mathematical roots of differential cohomology. So we'll start very early in the game. Well, I'm stuck. There now. Okay. So we'll go back to 1948 with the Gauspinate Theorem. And, well, it's the famous Gauspinate Theorem. If you integrate on a closed two-dimensional manifold, the curvature, you get the Euler characteristic, chi of m. And, well, that was a great theorem. It's still a great theorem. Now, in 1943, Allendorfer and Weil proved a generalization of this to any closed orientable manifold. Of course, you can't do the curvature by itself, but you take what's called the Faffian polynomial, which it's an invariant polynomial on the special orthogonal group. It looks like this. If you take a skew-symmetric matrix and put it into this canonical form, you see it's a lot of little 2 by 2s, and you take the product of those just one number at a time, A1, A2, all the way down. That's invariant. You need the special orthogonal group, and it's invariant under the adjoint action. You plug the curvature into it. You can take the curvature form, omega, wedge it with itself in a certain way, make this characteristic form, make this form, normalize it appropriately, and then well, I don't have the right technique here to make this go ahead. Oh, I know why, because I'm pushing the wrong button. Okay, let's see if that works. There. There. So they proved that if you integrate that thing over an even-dimensional manifold, you get the Euler characteristic. However, the proof was complex. You needed to triangulate the manifold, embed each piece in Rn, and it was a long, complicated calculation. And they urged Chern to find an intrinsic proof. And this proof, which I'm going to go through because it's so simple in a way, really changed a lot of things in mathematics. And here was Chern's proof. So you can find a vector field on an even-dimensional manifold with isolated singularities, let's say those points, M1 to Mk, with the degrees of each singularity are D1 and so on. And it was well known, but the Euler characteristic of the manifold was the sum of the singularities of the vector field. So here was Chern's approach. So here's the sphere bundle, the tangent sphere bundle over M. And this characteristic form, when you lifted it up to the sphere bundle, you pulled it back by projection down, it became exact. It was D of something, which is p sub chi with a tilde over it. And that something involved the Riemannian connection, theta, and the curvature omega. Moreover, when you restricted this form, and it was, of course, a 2n minus 1 dimensional form, when you restricted it to the fiber, it was normalized so that its integral was 1. Okay? That was, and d of it was the pull-up of the characteristic form. So here was Chern's proof. He said, okay, so we'll integrate this form over the manifold. And he said, well, gee, I can leave out these isolated points. I'm still going to get the same integral. But when I do that, I can lift the integral upstairs, just push it upstairs, and integrate it up there by pushing this, the manifold minus the points, pushing that up to the sphere bundle. But gee, when I integrate up there, it's exact, so then that's the same as taking the integral of d of this over this guy. Gee, that's the same as the integral of d of this over the closure of that guy, but now that's equal to the integral of p sub p tilde over the boundary of the closure. Oh, what's the boundary of the closure? Well, it was just the sum of the fibers of those spheres topologically multiplied by the degree of the singularity. Since the integral over each of the fibers was 1, you got the sum of the degrees, and that's the Euler characteristic. So now this theorem, which took a number of pages, I suppose, it's a relatively short paper, but still it wasn't one page. But that was the idea. A very, very simple and elegant idea to get that result. And it set off I think, a wave in topology, which continued for some time. So Chern and Weil started to work together, and if G is a Lie group and script G is its Lie algebra, they looked at all these invariant polynomials, all the polynomials in the Lie algebra which were invariant under the adjoint action of the group. It's a ring, it had degrees, and if you have a principal G bundle over a manifold and it has connection theta and curvature omega, you can take any polynomial, any invariant polynomial, plug in the curvature to that, and what you'll get is a G invariant horizontal 2L form, even dimensional form on E. Horizontal means with respect to the connection. Moreover, since because it's invariant and horizontal, you could consider it as a form downstairs. It's closed.
What does it mean to be horizontal?
It means if you stick any vertical vector in, it vanishes. So it only lives on horizontal vectors. And it's invariant. So it really comes from a form down below. So we can think of P of omega to the L as a form, a horizontal form upstairs, invariant, or you can think of it as a form downstairs. It's closed, and they showed its cohomology class. So it's a closed form, so it represents some cohomology, real cohomology. It says contained in H2L of Mg. That's a mistake. It means H2L of Mr. Okay, there are a few errors in these slides, which I discovered. So yell out if you find one. But anyway, this is its cohomology class, and that cohomology class was independent of the connection. So it was topological invariant. And this only wants to go two at a time. So as I said, it's closed. The direct calculation shows that it's closed. And if you have two connections, theta 0 and curvature omega 0 and theta 1, omega 1, if they're two connections, you can join them by a curve of connections. That's also always the case. And you can take the derivative of that connection and with respect to t, and notice that that derivative is itself horizontal because the connections always take the same value on the vertical vectors, and so if you differentiate them, all it's left with is horizontal. And thus, you could plug theta prime into P and get a horizontal invariant form. So that's the lift of a form on N. And direct calculation, which I guess Chern and Weil must have done, shows that the difference of those two forms, two closed forms, one with respect to the first connection and one with respect to another, is exact. It's in fact d of this thing, d of this thing, the integral from 0 to 1 of L, what it has to do with the degree of these forms, and thus the cohomology class is indeed, now I have the R right there, it's indeed well defined and independent of theta. So this is the sort of the famous Chern-Weil homomorphism. We'll go on with that a little bit. Oh, okay, it didn't skip that time. Now it doesn't go at all. There it is. So what we had here is a map depending on theta, of the invariant polynomials into even closed forms on M, and just without now the connection from the invariant polynomials into even cohomology in the base. So these were all characteristic classes. These maps are ring homomorphisms. These invariant polynomials are a ring, and there's a ring structure in both of these things. And moreover, they're natural in the categories of principal G bundles with or without connections. So what you really have is, well, one thing you have is a map from the invariant polynomials into the even cohomology, even real cohomology of the classifying space of G, BG. And the collection of all of this stuff is referred to as the Chern-Weil homomorphisms. And it was, you know, it was great work. It was great work. And that was done very shortly after Chern had his monumental proof. So if we go back to this thing, which was the difference form, d of it was the difference, suppose you have another curve that joins those two connections. And so here we have one of these forms, d of which is supposed to be the difference, and here's the other one. Well, it's clear that it's closed. This difference is closed because each of these represents something that's closed, so d of each of them is closed, and they get the same answer. So d of this is 0. But in fact, it's actually exact. You can prove that this form here, is well defined. It's independent of the path that you chose joining those two connections. It's modulo exact. You know, this thing is well defined modulo exact. It didn't depend on what path you chose to connect the connections. And so what you can do is define this new form CS of P, which is this guy modulo exact. So it didn't depend on the path as the left-hand side does. And it's just a pair of connections. You'll get a form well defined up to exact. Now let me see. I don't know what.
You're not proving it, you're stating it.
Pardon me?
You're not proving it.
I'm not proving that,
You're
no.
stating it.
I'm stating it,
Okay.
and it's not a difficult calculation. But I'm wondering what I'm talking about here. I can lift this back to E. Oh, yeah. So, yeah. So here is this, this bundle. Here was the original thing. We can lift this whole thing back to E. So we can pull this bundle back up to E, and here it is, pi star of E, and pull the connection up. So now over E itself, over the bundle, the principal bundle, I have another principal bundle. And so everything lifts up there. But upstairs, in that bundle, it has a product connection because it's trivial when you lift it to itself because it has a typical product structure and a product connection. And the curvature of one of those, here's the product connection up there. The curvature of that, it's a product connection, it's a trivial connection. The curvature is 0. So when you go up there and you look at this CS term, the difference of the two connections, it really only depends on the first connection because the other one is trivial. And so you get a form, TP theta, upstairs in the principal bundle itself. In the principal bundle itself, this form lives, TP theta. And up there, and D of it is the lift of the characteristic form to the bundle itself up there, and that is exact. And here's a formula for it.
Comparing the product connection with the pulled up of the other connection. Is that
Yeah,
what you're saying?
yeah,
Okay.
yeah. So upstairs then, in the principal bundle, there's this form, D of which is this guy. And you can calculate it. There's a sum of a bunch of coefficients here times the invariant polynomial, and you plug in theta, and you plug in theta bracket itself, I times, and curvature, and you sum over all this stuff, and you get it. And so that's TP theta. It's a form upstairs. It's defined modulo exact, just like this was defined modulo exact. So it was a form upstairs in the principal bundle, defined modulo exact. And those forms turn out to be pretty interesting. And so it's when you restrict it, when you restrict this form to the fiber, when you restrict this form to the fiber, you can see that it's closed on the fiber because D of it is totally horizontal, and therefore it's closed on the fiber. So that TP theta restricted to G, restricted to the fiber, is actually in the odd cohomology of the group. So all this stuff is in the aegis of transgression. We started with cohomology classes in the principal bundle, in the classifying bundle, and we ended up with cohomology classes in the group itself of 1 degree off. These are odd classes. And so here are some examples. There's one, the Pontryagin polynomials. So we'll look at a couple of these. The Pontryagin polynomials. P1 over here is just the trace of the product of the matrices, normalized this way. And so P1, when you plug in curvature, what happened? There, I pushed the wrong button. Yeah. So P1, when you plug in curvature, is the trace of the wedge product of the curvatures. And TP1, this form upstairs, is this. It's the trace of the wedge product 3 times of the curvature minus 2 times theta wedge omega. And this form is popular among the physicists, this form. And I guess it's called the Chern-Simons form, but that's a special case of something much more general. So fooling around with this, I have to say this. Well, I'm now going to start with work that I did with Chern, and then I'll morph to work that I did with Cheeger, and then I'll morph to work that I did with Sullivan. So everything from here on, even though I kind of got some of it started, was joint work with 3 wonderful mathematicians. And so the motto is, if you want to do excellent work, work with someone who's even more excellent than you, and something good might come of it. So, suppose now we just have a 3-dimensional manifold, closed and oriented. Now, and here's its frame bundle. Now, the oriented frame bundle with the Riemannian connection. So we make a Riemannian manifold. Riemannian 3 manifolds are all parallelizable, so I could lift the manifold up into its own frame bundle. I could get a cross section. And then I could say, I have this cross section up there. I'll integrate 1/2 TP1. Because 1/2 TP1 happens to be an integer on the fiber. So I'm just going to integrate that and get a number, and I'll take it modulo the integers. Now, why do I take it modulo the integers? Because if I took another cross-section, homologically, that is just the original one plus some multiple of the fiber, plus perhaps torsion, although I don't even think there is any torsion, but maybe there is. So therefore, when you integrate over this second cross-section. Homologically, it only differs by a multiple of the fiber. The thing is an integer. This is an integer on the fiber. And so it's a well-defined map, well-defined function. Yeah, by integrality of the fiber, you can see it's well-defined. So this is a function, an R mod Z valued function, a circle valued function, if you like, which is on a Riemannian manifold. Now, it turns out if you differentiate with respect to a conformal change, you'll get the same answer. So it's a conformal invariant. And it turns out, here's a funny thing. So it turns out that a necessary condition that a manifold be conformally immersible in R4 is that this invariant is 0. Remember, it's a mod Z invariant, but that it's 0. So that's a nice result, because if you look, for example, at the three-dimensional projective space, real RP3, phi of it's a half. And thus you can't conformally immerse it in R4. But that's not so obvious, because pieces of it are isometrically immersible in R4, and the whole thing is immersible in R4, but not conformally. So you can't conformally immerse this. Now, this result is was funny to me, because I decided on an airplane with Jeff Cheeger, we were going somewhere. In fact, I know where we were going, but it doesn't matter. I said, I wonder what this invariant is for something that's just a hypersurface in R4. And I did the calculation in the airplane. It was pretty easy. I used quaternions and got a nice, you take the normal vector and you say I, j, k. You get a nice parallelization of the manifold. And I did the calculation. I said, oh, hell, it just comes out to be 0. And Cheeger said, what do you mean, oh, hell? I said, that's a theorem. I said, oh, you're right, it is. So I don't know, if he hadn't been sitting there, the obvious might not have occurred to me, but it occurred to him. So
the necessary condition.
You're right. So that's right. So this is a special case of much more general non-immersion, conformal immersion theorems that come out of this stuff. And here's one more thing about this function that I've always treasured, although I don't know what good it will do. But if you look at this is a function from conformal structures into R mod Z. So conformal structures is a big space, but nonetheless, there it is. So the critical points of phi, which is a pair, a manifold and a conformal structure, critical points are locally conformally flat. In fact, if it's a critical point, it's locally conformally flat, and if it's locally conformally flat, it's a critical point. So that characterizes the critical points of this function, and it would perhaps be appealing to follow the gradient of the function or something like that upstairs and see if you could always get to something locally conformally flat. I'll tell you now, not all three manifolds do have locally conformally flat structures, but they almost do. There's some degenerate cases. So it's possible that something good could be done with this. So in here, I reminded myself to say that these theorems, along with various generalizations, were joint with Chern. Okay, so I want to look at some more R mod Z functions. So we'll go back to the Euler class. We'll go back to the Euler class. I'm creeping up on differential cohomology here. So remember that we had this invariant polynomial, and the Weil image of it was a real integral class in the classifying space and so on. So now let's suppose I have a Riemannian vector bundle over M. So this is not the tangent bundle anymore.
Why don't you put Z there?
What?
Coefficient Z. You want that?
I do, actually.
Okay.
I want that Z right there. Because it's an integral class. Because things are normalized. So this is, it's the Euler class. So So let's take an even-dimensional Riemannian vector bundle, oriented, over a manifold M. So this is no longer the tangent bundle. This is just any old bundle. And you put a connection on it, theta, which preserves the inner product. And here's the associated sphere bundle of this guy. And now, downstairs, P sub chi, the Euler form, or the Euler class, is a real class, but it's the real form of an integral class. It's a real form of an integral class. Now, when I lift it up, it's exact. And following Chern, it doesn't have to be the tangent bundle. It's always exact. And its integral over the fiber is 1. Okay. So now, let's look at the homology sequence of this thing in the appropriate dimension. The fiber, the homology of the fiber, the only homology it has is in 2n minus 1. That injects into the homology of the sphere bundle. And the homology of the sphere bundle maps down onto M. This is a standard homology sequence of fibrations, of this particular one anyway. So now let's take a cycle.
Well, which fibration is this?
This is this is a sphere bundle of a vector bundle over a manifold.
Right.
Huh?
If the Euler class is non-zero, it's non-injective.
If the Euler class,
So the bundle is non-zero, then it's non-injective.
what's non-injective?
Homology of the fiber.
I think it is.
I know.
Well, what does that, why wouldn't the homology of the fiber?
You get the sequence, but you can't always put a zero there. I mean,
All right, well, it won't matter.
okay.
But, okay, that won't matter. I thought you could.
Okay.
I didn't remember.
Think of the half fibration over the two-sphere, right? The circle
Yeah,
maps into the three-sphere.
well, okay. I don't know if that
You
comes.
told me to correct the notes.
Yeah, all right, well, that's fine. But what I didn't really care, I wanted
You don't
it
care, right?
in there, and I wanted it to be the kernel of this map.
No, that's
So
true.
I wanted this to be exact at this point,
Right.
and I wanted this to be onto, and I believe that's true. I also believe this is true, by the way, but I'm willing to take correction from my betters in topology. So now, let's take a smooth cycle downstairs. Now, from the above sequence, we could lift this to a cycle upstairs in the sphere bundle with, because this homology is onto, so that we could find the cycle upstairs such that it's pushed down. By the way, see that star right there? It should be down there. I'm pushing down a cycle, not a pulling up a cohomology class. So, but the push down of that cycle is homologous to U because this maps onto, so mu is a cycle. So up to a boundary, we can find something upstairs. And now I'm going to define modulo Z, something I'm going to call chi hat of mu. And what I'm going to do is integrate this special form upstairs over mu prime and do a correction factor over alpha, because it didn't go right down to mu, by integrating the Euler form over that, the interior of alpha, over alpha itself, rather than the interior of the boundary of alpha, over alpha itself, and I'll reduce that mod Z. And from the exact sequence and the integrality of this over the fibers, you can show that this is well defined.
What's the dimension of M?
There's no special dimension. M has no dimension. Any dimension you like, M has. Okay. So now, what I've done, and so you can show that this is well defined up to an integer. I'm reducing mod Z. So now what I have here is a function of cycles in M, 2n minus 1 dimensional cycles, and I have a nice function of those cycles. And So here it says it here. So chi hat, associated to the Euler class, Euler character, maps all the cycles of M in a linear way, not a linear way, but preserving the group. It's a homomorphism from all the cycles into R mod Z. And if you remember the formula from the previous page, if the cycle happened to be a boundary, then the answer is you just integrate the Euler form over the interior and reduce that mod Z. And that's well defined. So this K hat carries more information. This chi hat carries more information than the Euler form itself. It says here, since knowing the mod Z reduction of the integral of a form over every smooth chain, and you do that because you just take its boundary, that already determines the form. We can see that chi hat determines this. So it carries more information. So let's look at one really simple example. N equals 1. I have an S1 bundle over M, and the S1 bundle has a connection and so on. It's a the sphere bundle of a two-dimensional Riemannian vector bundle over M. And now I'll take a closed loop, and I'm supposed to get a number. So what's the closed loop going to be? What's the answer going to be? Chi hat of mu. Well, it's going to be nothing but the angle of holonomy. Okay? We have a connection in this circle bundle. You go around, you come back, you twist through an angle, normalize that by 2 pi, and that's what this is. And let's prove that because it's very, very simple. So in this case, the characteristic form is nothing but just the curvature itself. It's just 1 over 2 pi times omega. And p sub chi turns out to be just 1 over 2 pi times theta, because as you may recall, d theta equals omega in this most simple case. So now I'll take a closed curve down here, and I'll attempt to lift it up to a horizontal curve up here, because I'm going to parallel translate all around. So here's the curve upstairs. It goes around and around. It comes back to the same fiber it started from, but it's gone through this twist. It's gone through this thing. So it doesn't come back to the same place on the fiber, because the holonomy in general is non-trivial. So now, when I integrate upstairs the 1 over 2 pi theta along this, well, it's 0 everywhere along here because theta is a vertical form. So this is a horizontal curve, except for here. And when you integrate it, you get exactly the angle of holonomy. It could have been a flat bundle, but you'd still get an answer because you could have a flat bundle which still has holonomy. So we could have had omega equals 0. So we can see in general, chi hat carries more information than does the form whose boundary it is upstairs. So, then there's that form. Okay. So, in generalizing this stuff, in 73 with Cheeger, we defined something called differential characters. And this is where I was going to stop in this. How much time? Is this a good time to stop?
If it's a logical stop, then it's fine.
It's a logical stop. I'm going to stop.
Okay, let's have a 15 minutes break.
Yeah, 15-minute break. Does anyone have a question?
Well, you can.
Yes, I have a question.
All right, go ahead.
So, I know what is spinor structure on a manifold.
You know what is a what?
Spinor structure.
P.
Spin structure.
P. P.
Spin.
Spin.
Spin, yeah.
Yes.
I'm not familiar with the definition with the notion of conformal structure.
Oh, a conformal structure is just an equivalence class of Riemannian structures up to multiplication by a function,
By a function.
positive function, yeah. Yeah, that's just a conformal change in the metric.
You keep the angles.
Yeah, it keeps the angles, changes length, but it doesn't have to be a constant. It can change all over the place as long as it's positive. Any other questions before the break?
Can
Another question. Go ahead.
that, so to fix a conformal structure, so to say, could this be expressed in terms of principles, in terms of principal bounds?
Well,
So spinor structure could be expressed in terms of reduction of the, so we take tangent bundle.
yeah,
So first we reduce its structure to the orthogonal group, to special orthogonal group.
yeah,
And then we leave this structure to spinor group.
to the spinor group.
To the spinor group.
Yeah, but it might not be a spin, it might not have a spin structure, the manifold.
Might not have. Yeah.
Right,
Yeah, but it has, then spinor structure means that we choose a leaf.
yes.
But what about conformal structure? So could it be expressed in kind of this term?
I haven't thought of that question.
It
Maybe.
has a simple answer. In other words, you reduce the structure. If you have a smooth manifold, the structure group is GLN.
Yeah.
Yeah,
If you reduce the structure group to the similarities,
Right.
it's a conformal structure. That's the answer he wants.
Okay.
oh,
The
okay.
similarities, orthogonal plus dilation.
Yeah, 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 yeah. Yeah, it's, yes,
Reducing
That's
to the
all.
orthogonal group is like a metric up to a constant,
right,
and then reducing to a similarity is
Yes.
a conformal structure.
right. But that is different from a spin structure.
Yeah, but he wanted to explain what his question meant by making an analogy with spin structures. So he's trying to.
This is funny.
Any other questions? So the functions that we described before were functions on cycles, particularly the last one, taking values in the circle. And when the cycle was a boundary, it was the integral of something over the interior. So that made us make this definition. So if we have a differential form and a chain, we're going to write omega bar to evaluate on that chain means it's integral over the chain modulo z. So that's what omega bar does. If you take a differential form, you want it to be a cochain, in effect, mod z. And by the way, if you think about it, that already determines the form. So if something integrates to an integer over every chain, it's zero, because you could just integrate it over a very small chain, and obviously it's not going to be an integer, so it has, and if it's zero over everything small, then it's zero. So anyway, that's omega bar. So now we're going to define an abelian group here. So zk is the abelian group of smooth k cycles, and we're going to define h hat, upper k of m, it looks almost like cohomology except it has this hat on it, is functions that are homomorphisms of the cycles into R mod z, but with the property that if the cycle is a boundary, f of a boundary is the integral of a form reduced mod z. So it has a very special property when the cycle is a boundary. It's the integral of a form reduced mod z for some omega sub f, for some form, k form. These are functions of k minus 1 dimensional cycles. And this group we're going to call differential characters. Now, from the definition, it's easily seen that omega sub f is closed, that omega sub f has integral periods, and that omega sub f is uniquely determined by f. Those are easy things to check, and if you'd like to do them, check it, you're welcome to do so.
So the logic, though, is you assume omega sub f exists, and then it has these properties.
Yeah, yeah, you assume there is such an omega sub f, and then it has to have those properties. And so that's what this case is. Now, it turns out there's a lot of them. There's a lot of them. So bar is going to, up here, is going to denote reduction modulo z in general. So now if we have one of these differential characters, f, since the r is divisible, or maybe it's because r mod z is divisible, but because there's enough divisibility around, we can find a real cochain whose reduction mod z restricted to the cycles is f. You can just extend this t and lift it and so on. So you can always find that. Now, if I look at the boundary of this real cocycle and reduce mod z, well, that's the same as, if you think about it, taking the boundary of the cochain already reduce mod z, and that, since that on cycles is this, that has to be f on the boundaries, and that is the reduction mod z of a form, which we had already determined was closed and so on. So that means that if I subtract this from this, I'll see that omega sub f minus the co-boundary of t, reduce mod z is 0, and that implies that omega sub f minus the co-boundary of t is an integral cochain. Moreover, that cochain is, if you just look at this formula, the cochain is closed. So therefore, it's a cocycle. C is we've defined a cocycle right here, an integral cocycle. And if you follow this stuff through, change t by something else which does this, it's easily seen that the cohomology class, this integral cohomology class determined by C, is independent of the choice of t. And so I'm going to set eta sub f into this C. And so eta sub f is an integral cohomology class, and because of this definition, you can see that its real image is also the cohomology class represented by omega sub f. Remember, omega sub f has integral periods. It represents a real class with integral periods, and the real image of this is equal to that from the definition. From the definition. So now, let's suppose we let wedge k, for any k, sub z be closed forms with integral periods. Okay? Then we see that delta 1, so now I'm going to define a map. Delta 1 takes hk hat into this wedge kz. Delta 1 of f is omega sub f, the original omega sub f. And delta 2 maps into the integral cohomology. Delta 2 of f is mu sub f, or I think it was eta in the previous page. Was it eta in the previous page? It was eta. And on this page, it's morphed to mu, but try to remember it's really eta. That's another little error.
Morphing going on.
There's a lot of morphing going on, that's right. So let's see. So suppose I just have an ordinary differential form, and I take a cycle. I could just integrate that form over the cycle and reduce mod z. I could just calculate rho bar of alpha. Now, of course, on a boundary, it's the mod z reduction of d rho. Well, d rho is certainly a closed form with integral periods. In fact, it has 0 periods. So rho bar is an element of this h hat upper k. It's just an ordinary differential form. You integrate it and reduce mod z. Now, rho hat equals 0 if and only if rho is already closed with integral periods. So going down here, and here's a major error. No, here's a major error. Anyway, let's stay here for a minute. So that's something that's inside. We found something inside here. We also can note that R mod z cohomology of dimension k minus 1 is also in here. After all, R mod z cohomology is just hom of homology into R mod z. It vanishes on on boundaries, so it's in here too. So I can thus stick two things. I can inject two things into h hat. One is the R mod z cohomology, and the other is not forms with integral periods, but it's wedge k minus 1 modulo this. So this is also an error. These notes are from a talk I gave a few years ago, and I messed them up then, and I didn't realize that. I didn't remember that. So here it's messed up here, but the next page will make it clear. So, goodness. So, well, here. So now here is a diagram. It's a commutative diagram with our friend HK upper hat. I hope he's your friend by now, sitting in the middle of it. And we have delta 1, that's the map into the forms with integral periods, closed forms with integral periods. That's omega sub f. We have delta 2 now. We can map it into integral cohomology via that other thing, delta 2. Both of those go into the real cohomology. The integral cohomology goes into the real cohomology, and these forms with integral periods go into real cohomology. And this is commutative, this little diagram is commutative. Now, it's also the case, as we saw, that R mod z cohomology injects into this. But it also maps by the Bachstein map into integral cohomology of the next dimension up. And it turns out, if you look carefully, this, if you put it in there and do this, that is the Bachstein map, or possibly it's minus the Bachstein map. So, but don't worry about that. So, and this is commutative. Now, we also had this thing, just plain old forms, modulo those that are going to vanish when you integrate them and reduce mod z. We have those forms, and they inject into there. But we also map this into omega sub f, into delta 1. But that, as we saw, is just the differential of this thing. So this is commutative. This is commutative. Now, almost fine.
Definition? Oh, sorry. Okay, I got it.
Right. Now, on the left, the k minus 1 dimensional real cohomology obviously goes into the R mod z cohomology by the standard map, the coefficient map. And by the de Rham cohomology, it goes into here. It certainly goes into here. It's up here, it's closed forms. These are closed forms with integral periods, but this lives here. And this, if you follow it through, is commutative. And finally, if you look at the definitions, you can see that the kernel of this map is exactly this. This is in the kernel by the definition of, well, you follow it through, it's in the kernel, and it has to be the kernel. So this sequence, and this is onto, so this is great. One can construct a differential character which maps into any integral class you choose. So this map is onto, this map's an injection, and is the kernel. So this diagonal is exact. By similar reasoning, this is exact. After all, this thing vanishes on all interiors, so it's clearly not going to give you anything much of a form. In fact, it's going to give you 0. It's exact here, but it also injects. And again, it's onto, one can show any closed forms with integral periods would come from something up here. You could make one up that would do it. And so we have this. Now, on the other hand, upstairs is the Bachstein sequence. It's a piece of the Bachstein sequence. So this is an exact sequence on the top. Not a short exact sequence, but it's an exact sequence on the top. And so is the bottom an exact sequence. It's just a de Rham sequence. And this is an exact sequence. So now I have this commutative diagram of functors, and these are all natural transformations. So this is quite a nest here. So what we have is that the characters, these differential characters, sit inside this network of guys, all of whom are familiar. Just differential forms, forms with integral periods, R mod Z cohomology, real cohomology, etc., integral cohomology. And right in the middle is this guy. Okay. Now, in fact, we might say, well, how much extra information is this really carrying? It's telling you about integral cohomology, fine, it gives you that. It's telling you about forms with integral periods, fine, it's giving you that. And such, the image in both cases, in the two cases, are connected by this. They both represent the same real class. Well, is there any more information in this guy than just this and this? Well, for that matter, just this and this. These two things are inside it. Maybe that's all there is. But I'm happy to announce that it's not determined by just these two things inside. It's not the whole thing. And it's not determined by the things that it goes into. In fact, here's one way to squeeze this down. And this is a short exact sequence. So on the left is a torus. It's the quotient of real cohomology by the image of integral cohomology. So it should have had a little real image in there. So this is a torus. That maps in here because the real cohomology went to 0 on this map. This map is into pairs of integral cohomology and real cohomology and forms that have the connection that the real image of this represents this guy, the class represented by this guy. And so this is more than the right-hand side. This is the two right-hand sides glommed together. And thus, it says it's determined by eta sub f and omega sub f, but only up to elements of a real torus whose dimension is the k minus first Beatty number. So if there was no Beatty number there, it would be that's all it would be as a form and everything, but it's not. Okay, so let's look at some examples. So what's H1? Well, that's just C infinity maps of M into the circle. Okay, that's a perfectly nice thing. And it turns out that H2 hat is isomorphism classes of circle bundles with connection. So that already is interesting. And it's really represented by the angle of holonomy. If you know the angle of holonomy of a circle bundle, you know the isomorphism class. You can put up a connection and get a connection on there, and it'll be determined up to isomorphism. And so that's H2. a perfectly good thing. And we saw that when we looked at the Euler character, that simple version of the Euler character. So here are two examples, and that's perfectly nice. Let's see what's next. Now, so here's the thing, and we'll go back to the Chern-Weil homomorphism. And it turns out it lifts to a map into H hat. Now that's not a trivial statement. So we'll look at pairs of an integral class in the classifying space and an invariant polynomial such that the real image of this integral class is the Weil image of that invariant polynomial. So remember, invariant polynomials on the Lie group, in the Lie algebra, give you elements in the cohomology of the classifying space. But there are integral classes there. There may be some torsion, so there are integral classes there that, that map into that Weil image. So look at such a pair. That pair forms a group. In fact, it forms a ring. And there's a unique natural map from that space, the invariant polynomials together with integral classes, we'll call W hat, into the H hat 2L, into differential characters, such that the delta 2, if you follow that map with delta 2, you get the characteristic class, the integral characteristic class of the bundle that came from eta in the classifying space, and you get the differential form that came from P. And I stated here, but this is a ring homomorphism. So this is not trivial to prove, but there it is. It's a theorem. And I want to go back.
So there you want to take the direct sum over L or something like that.
Yeah. Yeah. Well, I just did. That's right. It's a ring homomorphism if you take the direct sum over L. I want to go back a moment because I forgot to mention something. In fact, I'm going to go back. I've characterized H hat as an abelian group, but actually it's a ring. And the ring structure is interesting. Here's how you multiply in here in the cases that are easy. So, for example, this sits in there. How do you multiply any character by it? What would be, so I have a character here, and I have a guy, some other character here, and I have one inside, which is actually an R mod Z cohomology class. And the answer is, you take the Bachstein of this guy, getting an integral class, and you cup that with delta 2 of the character, and you'll get another R mod Z class. Here, you wedge with D of this thing. It's theta wedge D theta, which is a ring. But there's more to the, so how do you really multiply two characters? And I'm not going to go through the formula, but it comes down to a nice result of Curvaire, which, and Dennis was more or less alluding to this morning. Pardon me? Yeah. That the limit of cup under subdivision is wedge. So if you have two forms and you think of them as differential forms, but you don't think of them as forms, you think of them as cochains, right? And you can cup them. You can take the cup product. But the cup product is not the cochain represented by the wedge product. It's close, but no cigar. That's an American expression. But if the cigar used to be a big prize for people at a fair, you know. So, but if you take the limit of that difference, cup minus wedge, under subdivision, an appropriate kind of subdivision. It has to keep cells fat enough. They can't just get too skinny. Curvaire showed that limit is 0. Cup minus wedge goes to 0 under subdivision. And that is the key to the multiplication in here. You write down a formula including cup and wedge, and it all looks fine, except it's not a character. But when you take the limit, everything gets good, and it's a nice product. That actually was proved separately by Jeff. He wrote before we wrote the big thing up, he wrote a separate paper showing that multiplication. So there it is. So this is really a ring, and it's a graded ring. HK times HL is an HK plus L, and so on. So fine. What?
Silly question.
A question.
A question.
Right in the middle of the talk, but that's fine. Go ahead.
In Russia, it's,
You're entitled. What's the question?
so you described H1
Yes.
hat, and you described cup product somehow now.
Right.
So with values in H hat 2. So
Yes, if I take the product of two guys in H hat 1, I'm going to get something in H hat 2, which is correct.
Yeah, but so is it easy to explain how the product works in this?
It's a wonderful question. It's a wonderful question. And as I recall, the answer is, so now I have two functions into the circle, and I want to multiply them together somehow to get a function that takes a cycle into the circle. Now, as I recall, I worked out the formula for that. So it's a perfectly reasonable question. You take delta 1, you take the form associated to one of them.
DF.
Yeah. You multiply it by the function. Now you take the function, and so now I have a cycle. Like, let's say it's a circle itself, and I'm going to go around. I want to integrate something over this circle, and I believe I lift the function to some real valued function on this circle, and I integrate that function times d of the other guy. And that turns out, and then I take that modulo z, and that turns out to be commutative or anti-commutative. It turns out to be well-defined, and I believe that's the formula. If you give me your email, I'll send you the proper answer, but I think that's it. But it's a great question, because once we saw it's a ring, I remember saying, well, how the heck do you do this? And then that's what came out. So it's kind of nice. You have two maps of the circle into itself. Let's just say we just do this with the circle itself. I have two maps of the circle into itself, and I can put them together to get a number in R mod z. So I can put them together in some sense and get a point on the circle. And you know, it was not so obvious how you do that. And but you can, and that's how you do it. I mean, they have to be smooth maps of the circle to itself. Okay, so this is a ring. I gave you examples. Where are we? We've lifted the Chern-Bay homomorphism. It's a ring homomorphism, and so now we can look at a bunch of examples now that we've lifted this thing. So for every so now in SO, oh heck. There we are. I pushed the wrong thing. So we've already seen in SO2n we have we have the Euler class together with the form, the integral Euler class together with this form, and this goes into that chi hat, which I already defined. We can take the unitary group and look at the Chern classes. We have to make sure that they're integral classes. And here's the big C, the polynomial, the Chern polynomial. And again, we get a character, a differential character corresponding to each of the Chern classes, the actual integral Chern classes. And the same thing.
You need a connection on something, right?
Yeah, you need a connection. You need a connection on the bundle, just as you did. Yeah, you needed a connection on the bundle. And you get these guys. And similarly, you get the Pontryagin guy. And going back to the theorem that talked about a three-manifold, when we lifted it up, we got a cross three-manifold with a Riemannian connection. We lifted the manifold to a cross-section in the bundle, and we got that formula phi. That was really the evaluation of P1, of 1/2, as it turned out, P1 hat. So so all these guys, and the fact that this is ring homomorphism gets useful applications to the conformal immersion theorem. It relates to the Ada invariant, and it relates to flat bundles. So this is a pretty good result. I'm pleased with that. I want to talk about flat bundles a little bit because these things exist in the case that the bundle is flat, if omega is 0. Now, all flat bundles come from representations of so this is a principal bundle, G bundle over M, with connection, but it's flat, okay? And all those come from representations of G in the fundamental group of M. Those representations really tell you what holonomy is around a closed curve. And since omega equals 0, the Weil homomorphism of this guy, they're just going to live in the R mod Z cohomology. So we get all these R mod Z cohomology classes depending on the various characteristic classes of G. And by naturality, these lead to R mod Z classes in the classifying space, okay, of G0. So if you think of G0 as a discrete group, think of it as a discrete group, not as a Lie group anymore. Forget that it's a Lie group. Just think of it as a group. Groups have classifying spaces. And so these things all lead to R mod Z classes in the discretized version of G. And
So why do you get in the odd homology of R mod Z? Go back to that line, omega 0, then what?
Omega 0.
Yeah, why is that?
Odd, because they're all odd classes, because it's one dimension less than the form.
Oh, it's omega hat.
It's omega hat, yeah.
Oh, right.
It's omega hat.
Okay.
They're all odd classes there. Now, they turn out to be what's called Borel classes in the bar resolution. So, and some of this, one way or another, was due to Wigner, the younger, who looked at the Borel classes in these discrete, quite important, interesting. They're measurable classes in the bar resolution. And for example, the CI hats generate all the cohomology, all of the cohomology in that discretized group. So it's a very rich family of classes, turns out. So let's see. I'm going to give an example. So just to remind me, a K simplex in the bar resolution is a sequence of group elements, one more than K. We make them equivalent. Two such things are equivalent if you can just multiply through by an element of the group. And these are the simplices. The boundary is just the alternating thing that you might expect. And that gives you boundary square is 0, and that gives you a cohomology theory or homology theory, I guess, in there. Now, I want to express chi hat, we'll take the easiest one, as an element of the 2n minus 1 dimensional Borel cohomology of the classifying space of a discretized special orthogonal group. Okay. So I want to do it right in the bar resolution. I want to show how you get that in the bar. So fix a point in the sphere, in the 2n minus 1 dimensional sphere, and we'll call a simplex generic if when I apply each of the gi to this element E, let's say the North Pole, I get a basis. I get linearly independent. And such generic simplices form a dense open set. Almost all these guys. It's just like if you take a random set of vectors in the sphere with high probability, like probability 1, they're going to be independent. They might not be, but there it is. So those are the generic simplices. And now I'm going to look at this. So since they're generic, they determine a unique convex-oriented geodesic simplex in S2 minus 2n minus 1. There it is. Here's S3, and here's a nice simplex with vertices on these 4 points, which were the movement of these G0, Gn minus 1. And now I claim that the value k hat of on any simplex is the volume of this guy, of this simplex, this actually geometric simplex, divided by the volume of the sphere modulo z. So it's what fraction of the sphere's volume is represented by that. Now it's quite easy to see, but this is a cocycle, and it's a Borel cocycle. It's defined in all these things.
So Borel means that this has to be defined almost everywhere?
Almost everywhere, yeah. Yeah, basically, almost everywhere. So k hat, so it maps the homology, the 2n minus 1 dimensional homology, into the circle. Now, not a heck of a lot is known, I think, at least didn't used to be, about the homology of these discretized Lie groups. But actually, it's a pretty interesting question. I say right here, the range of chi hat is an interesting question. What is its range? It's taking the homology and sticking it into the circle, sticking it into R mod z. For example, if the range contains an irrational number, you know that there is some rank in this group, right? Because if you get an irrational number, well, no multiple of it is going to give you 0, and therefore no multiple of it could be homologous to 0. So the range of this chi hat.
So that means the Borel homology of the SO2n with the discrete topology. Is that what you mean?
Yes.
Okay.
Yeah. It's the bar. It's the.
Well, bar constricted the abstract.
You could just do it within the bar resolution. It's the homology and cohomology of the bar resolution of this guy. So here's something that a result. Okay, so let's see. So first of all, it's easy to see, I claim, that the range of chi hat, it contains all the rational numbers. I don't recall why it's easy to see, but it is. And I think you can just make up some guys that'll do that. So the range contains all rational numbers, mod z. Well, does it contain anything else? Is it giving us any, what I want, real information? So we recall that a geodesic simplex has a bunch of dihedral angles. In fact, k plus 1 times k over 2. Dihedral angles are the angles between adjacent top-dimensional faces. So they're the top angles. And these determine its geometry up to a rigid motion of the sphere, so we might as well just think of a geodesic simplex as being determined by its dihedral angles. Now, for example, if I want to know this number in the two-sphere, namely the fraction of the volume or the area of a two-sphere represented by a simplex with dihedral angles alpha 1, alpha 2, and alpha 3, and I want to know its volume divided by the volume of S2, well, this is the Gauspinate part of the most elementary of the Gauspinate theorem, and it's a very nice rational function, at least when you divide by pi. It's a half minus a half times the sum of the angles. You know, it's just a, so that's a nice, I say it right here, it's a nice rational function. However, I'm not so interested in S2, I'm interested in an odd sphere. And as soon as you go to S3, what happened to my pointer? Here it is. As soon as you go to S3, the volume function is a transcendental function of a dihedral angles. That was first calculated by a German guy, I'm trying to think of his name. Anyway, it's a relatively complicated formula. It can involve the dilogarithm if you look at it a certain way. Anyway, it's not a simple guy, that formula. So we'll call a simplex rational if each dihedral angle is a rational multiple of 2 pi. So let's look at rational simplices. As we saw before, a rational simplex on the two-sphere has a rational fraction of the volume of the two-sphere. But what about the three-sphere? So here's a theorem that's due to Thurston. I first met Thurston at the Institute for Advanced Study, and I told him I was thinking about the volumes of spheres and rational simplices, and said, and so within, it seemed like lightning, but it probably took him a day or two, or maybe 3. He made a construction, which I'll never forget, and it ended up with this theorem. So in S3, all but a finite number of rational simplices, for all but a finite number, you can find an integer m, you can find some m, such that the fraction of the volume it represents is in the range of chi hat. So a rational simplex by itself doesn't represent a cycle, but he could manufacture a cycle, and it was very clever. And so all these guys are in the range. The volumes of all of them, almost all of them, all but a finite number, are in the range of this chi hat. So thus, the range of chi hat contains irrational values unless all but a finite number of rational simplices have rational relative volume. Well, so far, not a single example, there's not a single example of a rational simplex with irrational volume. So on the other hand, when you look at the formula for volume, you would think they almost all have irrational volume. But people have constructed some and so on. They keep constructing them, examples of ones which do have rational volume as a fraction of the sphere. But one would think that most of them don't. And I have to say, working with Jeff Cheeger on this problem practically, well, it did almost drive me out of mathematics. I really wanted to find an answer to it. I wanted to find a rational simplex that had irrational volume. And I didn't have anywhere near the background or anything else to even consider the question. I considered it for 2 years. Jeff said, I'm never going to work with you again.
You had to look for another
right. So I said, to heck with it. So, so if any of you wants to figure out, come up with one, it would be very nice indeed. It's related, obviously, to hyperbolic things as well. I think it's really a problem in SO2NC, which unifies a lot of these questions. And so these volume questions are very hard.
Excuse Excuse me, isn't it true that Hans Saul worked on this and related it to other conjectures, like Borel's regulator conjecture and things
I
like
think
that?
so. I think so.
I think there's a lot of still, it's equivalent to a number of other conjectures.
Yeah, I think it probably is. It's really a very good, it's really a very good question in mathematics.
Other Borel.
Okay, so now I'll get into my third collaborator who's sitting here. So I want to go back to the diagram. There. So there's a diagram. Now, as I said, this is an unfamiliar thing nested into all these familiar things with these exact sequences and so on. And one might rationally think, how many such functors could there possibly be? I mean, is the world full of things that fit into such a diagram? And so the answer is no. No, there aren't. In fact, it's the only one. So there are other functors in the smooth category that have been developed and that are isomorphic to H hat. And they've all been isomorphic. Harvey and Lawson and this guy Zwick and made up some such functors. But in each case, they showed, yeah, but this is really isomorphic to H hat. So, and as it turns out, Deligne cohomology in the smooth category is also equivalent to H hat. Now that's an interesting fact because Deligne developed Deligne cohomology, probably not with the smooth category in mind because he was doing algebraic geometry, but nonetheless it came out. And it was in about the same time frame. But neither of us realized that there was this relation until sometime later. But there it was. So you can make up such functors, a model for such a functor, but they all turned out to be isomorphic to each other. They all satisfied the character diagram. And it turns out that the diagram itself completely determines the functor. So, Dennis and I proved that. So it's not a shock, but it was nicely done. And Dennis did the hard part, and I did the easy part. But nonetheless, there it was. And so this is unique. Now tomorrow, maybe. Okay, here's the theorem. Okay, good. In the smooth category, any z-graded functor together with the maps which satisfy the above diagram is equivalent via a unique natural transformation. Not only are they equivalent, but there's a unique natural transformation which makes that equivalence and makes, so anything that fits in there is uniquely, any imposter, a G hat. How did you get in there? Turns out G hat is naturally isomorphic to H hat. And not only that, the ring structure, which I don't mention here, is also unique. There's only one ring structure which would fit with the obvious multiplications of the guys inside and so on. So there's only one ring structure, there's only one such functor. So maybe, and I won't go through the proof, maybe tomorrow we'll talk about something. Hopkins and Singer in 2005 showed that similar hat functions could be constructed for all generalized cohomology theories. So this kind of a functor, and this is what's become the subject of differential cohomology. And tomorrow, maybe, Sullivan and I will construct two. One would be enough, but we may do two for K, for K theory, at least for even dimensional K theory. There's a very nice functor. It has a diagram just like the other one, except that the things that are appropriate to K theory, and we may even construct or talk about a second one. So that's the end of this lecture.
Thank you very much.
Okay.
Questions, please.
Yes? This is our questioner. We planted here and there. We needed someone to ask questions. We said, would you please ask questions?
Yes, and
It's good.
Even in the middle of the lectures, of lectures. So
Yeah.
my question is this. So you indicated that a kind of dealing cohomology, in fact, does coincide with H hat. Is it the case?
Yeah, if you look at Deligne cohomology, now I'm not an expert on Deligne cohomology, but I'm assured that in the real category, that it's a functor which is isomorphic to this one.
Okay.
Yes.
So you gave formulas, so you gave examples for H1 hat and H2 hat.
Yeah.
But usually the third is also an interesting one. What about H3 hat? Is there some nice picture for it?
Not that I know of. Not that I know of, but I haven't thought about that question very much. I've not thought about that. Yeah?
One more.
No, as many as you want.
So Sullivan indicated that perhaps there is a link between your conjecture about the volume of the simplices
Yes,
with rational vertices to some other conjectures.
yes.
And the simplest from, does it relate somehow from your viewpoint to Blow group or to another terminology to indecomposable elements in the third K group?
An indecomposable
Indecomposable elements
in,
in Quillen's K3 functor of complex numbers.
I don't know.
You know,
I don't
because
know.
the regulator.
Do you know,
I couldn't understand. Relate to what?
Quillen?
Indecomposable elements. So it's very difficult to construct a non-zero indecomposable element, specific one, in K3 Quillen. In the
K3 of?
K3 of Quillen.
Ah, Quillen K theory. Huh?
Of complex numbers or rational numbers.
Yeah, I don't know that area.
This is related to dialogarithm, and this is related to block kind of groups and so on.
No, this Quillen K theory is sort of, you take this thing with the discrete topology,
Right.
and if you look at the rational cohomology of that and play around with it to get the homotopy groups, that's the Quillen K theory, at least ignoring torsion. So it is related. So,
Uh-huh, yeah.
I mean,
Well, it must
by
be.
definition almost. I
Yeah.
mean, by the definition,
Yes.
it can be related, but, yeah. think
I don't know.
we can-
Other questions? Actually, I have one question. Yeah, returning to three-dimensional manifolds, can you reformulate Poincare conjecture in terms of your functional capital phi and this class of conformal matrix, some critical points?
Well, sure, because any simply connected manifold with a which has a is locally conformally flat is a sphere.
Is the three-sphere.
Is a three-sphere. That's a result of he was the former head of IHS, Kuiper.
Corporate developing map, yeah.
Right. So that's a nice theorem. So if every simply connected manifold has, you can follow the gradient and get to something that's the gradient of this phi function, you'll get to something that's locally conformally flat, and then you're done. And I thought, oh, just take a couple of pages, and then we'd have that theorem years ago, but no.
So the reformulation is the Poincare conjecture is equivalent to the proof that your function has a critical point. That's the reformulation.
No, but exactly.
So it's equivalent.
Single critical point.
At least one.
At least one.
That's all. It's equivalent to that.
That it has at least
There's a
one.
critical, his functional has a critical point if and only if the Poincare.
Okay.
That's correct.
Okay. Let's then speak again.
Okay.
The beautiful lecture.
Thank you.